Welcome to the Early Career Professionals in Mapping webinar series. The American Geosciences Institute has partnered with the National Cooperative Geologic Mapping Program to highlight the work of early career geoscience professionals, especially as it relates to the use and production of geologic maps. Each webinar will begin with a presentation from an early career geoscience professional, followed by an interview. Today's speaker is Becky McCerery from Northumbria University. She will talk about her research with glaciers and how glacial mapping can help in our understanding of climate change.
Hi, I'm Becky. I'm a postdoctoral researcher at Northumbria University, and I'm primarily a glaciologist, and I use mapping, particularly geomorphological mapping, to better understand the glacial landscape and how those landscapes might change with climate change. So today I'm going to start by giving you a brief introduction to my education background, and then we'll basically run through a case study of one of my recent mapping projects. So we'll explore the importance of glacial environments, how they shape and change the landscapes. We'll then look at how we plan for fieldwork and the considerations we need to make working in the remote Arctic, and then I'll show you the processes that we go through analysing our data and what those final outputs might look like. So growing up, I was really interested in the natural world, and after finishing school, I applied to Northumbria University to do my bachelor's degree in geography. And it was here that I first started to explore mapping as a potential career pathway, as we had lots of courses in geographical information systems and remote sensing. Then for my final year thesis project, I worked on creating glacial geomorphological maps of an area of the Lake District to determine where had been glaciated during the last glacial maximum. And then after this, I also did my PhD at Northumbria. And here I'm at the distribution and transport of natural oils by a previous ice stream during the last glacial maximum in Canada. More recently, I've been exploring the microbiology and weathering processes and glacial change in Arctic environments, which have all required some mapping elements to those projects, providing important landscape context to our understanding of glacial environments. So my mapping work now typically focuses on the geomorphology of the landscapes I'm working in, which in my case is the Arctic, to get a better understanding of the glacial processes happening there. For a bit of brief background, glaciers are large masses of ice typically found in the poles, so the Arctic and the Antarctic, as well as high mountain environments like the Himalayas and the Alps. Now, these frozen rivers of ice, they flow under their own weight due to gravity, and the way they move and flow impact on the landscape, changing over hundreds of thousands of years. These flow processes that are happening beneath glaciers can leave a landform record, and we can determine what some of these major processes are by what we see in the landscape. So there are two main ways that glaciers can alter the landscape. That's by erosion and by deposition. Now, glacial erosion covers a number of processes which crush, wear down and transport rock at the bottom of the glacier. Some of these processes, like plucking or quarrying, break up the underlying bedrock underneath the ice, and then that rock can be transported by the ice. And this transport can smooth and scrape other underlying rocks by rock-rock contact. And this acts a little bit like sandpaper, which polishes and smooths the rock, leaving behind surfaces like this one in the bottom left. Now, an important feature of some of these glaciers is the presence of meltwater at the bed, and this occurs where a glacier is warm-based, which means that the ice is not frozen to the bed year-round, and overlying pressure of the ice can allow the ice at the bed to melt, creating liquid water. In glaciers where meltwater can form, that water can also contribute to erosion of the rocks by enhancing chemical processes like weathering, as well as allowing these other erosional processes to occur more frequently, as that water allows the glacier to move faster over land by lubricating it. A glacier that doesn't have this meltwater at the bottom is called a coal-based glacier, and they are generally frozen to the bed year-round, so they move much slower and it's much more difficult for those erosional processes to occur. The other key process glaciers can shape the landscape with is by glacial deposition, and this occurs where rocks and sediments underneath the glacier, known as glacial till, as well as surrounding rocks and sediments at the glacier margins, those that fall on the glacier surface, are all transported and pushed around during glacier flow, and they're left behind as that glacier recedes. And these sediments can be deposited by melt out, so the ice melts around the sediment deposits, or they can be deposited by the ice pushing and squeezing the material beneath the ice and at the margins. So there are two main types of glacial depositional landforms. The first is ice marginal, so they occur at the edge of the glacier, and they mark past extent like these terminal moraines in the image in the bottom left. And these have been pushed into these mounds at the edge of the glacier and mark where it used to lie in the landscape. And then there are also subglacial landforms which form actively underneath the ice by flowing water. And we can see how these different conditions in a glacier, so whether it is cold-based or warm-based, and whether there's any melt present, might start to influence some of the landforms that we see in the landscape. So what we can do to determine past glacial conditions is look at the landforms that have been left behind and how they were formed, which is the geomorphology. And the geomorphology tells us what landforms and processes have occurred in a particular place to alter the landscape. They link together the landform and processes, and the geomorphology of different glacier types can then tell us a little bit about a glacial land system, which tells us more broadly how different types of glaciers, like warm-based and cold-based, can create different suites of key landforms. So we can identify past glacier dynamics and make predictions about the future state and fate of glaciers based on the landscape that those glaciers have left behind. So in the active warm-based glacier geomorphology, we typically see push, dump and squeeze moraines at the glacier margin, which are formed at the very edge of the glacier, and they tell us how long the glacier used to be in the valley. So we can see here on the left, these lumpy looking ridges here mark where this glacier margin used to be. So all of this lake type area was previously covered by ice. Then in warm-based glaciers, we also see subglacial landforms as well, and these are created by that meltwater that's generated at the bed of the ice. And we see landforms like outwash plains, so this greyish-looking sediment with meltwater channels inside it in the image on the bottom right. And these long stripes here called flutes, which form by sediment being washed into cavities in the bed of the ice. And all of these landforms require water to be present at the bed, causing the glacier to slide and transform the underlying soft sediment. Cold-based glaciers, by contrast, which are frozen to their beds, produce a different suite of landforms. So in this cold-based glacier, we typically see little or no subglacial landforms because there's no meltwater underneath the ice to create them. So the geomorphology reflects these processes, and what we do see is very thin covers of sediment over bedrock, which shows that not a lot of rock erosion and deposition has taken place. We can also see how the front of the glacier is starting to waste away here, so we aren't getting these big push and squeeze of deposited sediments, but this gradual decay and retreat of the ice front. But why does this matter, and why do we need to understand these different patterns of landforms? Well, we can use the emerging geomorphology to inform what's known as a land system. And a land system takes into account the typical geomorphology, so the pattern of the landforms, the sediments and their processes, to understand the glacier dynamics required to create that style of landscape. And these land systems, aided by geomorphological mapping, help us to understand how glacier dynamics might be changing under our currently changing climate. We can map past and present glacier extent to see how far glaciers have retreated. We can also map the landform and sediment record in front of the glacier that has been exposed by this melt. And this will tell us about the conditions beneath the ice, so whether it was warm-based or cold-based, and what that means for the future of these glaciers. So as our climate is warming, which is especially prevalent in the Arctic regions, more glacier melt and less snow is resulting in glacier thinning, and this is reflected in the landscape, leading to different suites of landforms. To start to explore some of these glacial land systems and how it links to a changing climate, we need to incorporate our knowledge and understanding into a mapping project. So for us, and the example that I'm going to introduce here, it was a really important aspect of our project to undertake fieldwork and see firsthand what these landscapes look like. So the first step in the project is then preparing for that field season. So picking a particular field site, undertaking any safety training, and then making sure that we've packed all of our appropriate equipment and clothes. Then the second step is actually undertaking that field work. So we're usually either camping or, in this case, living on a boat and undertaking our daily scientific tasks like recording the landforms, the sediments and the geology. Once we get back from fieldwork, we then get into processing that data and creating final outputs. So articulating what we see, mapping on software, and then interpreting those maps to see what they can tell us about the potential land systems in our study area and the changing landscape. So I'm now going to give you an example of how we developed that project, what we did in the field, and how we analysed data from a project in Arctic Svalbard, which is a small island close to the North Pole. So we chose Svalbard because it's especially sensitive to climate change. This is an area of the Arctic that is warming 6 times faster than the global average, and we wanted to see the potential impacts on the glacial environment there. So the aim of this project was to map loads of different glaciers and their geomorphology, and then develop key land systems which describe the style of glaciers we see on Svalbard and how they're changing. The first step in the project is identifying the study sites. So in Svalbard, which we can see here close to Greenland and north of Scandinavia, there are over 2,000 glaciers with lots of different properties. We have cold-based thin glaciers, thicker warm-based glaciers, which we've both explored before, but they also have these fast-moving surging glaciers, which switch between really fast flow and advance to slow flow and retreat on 10s to 100-year timescales, going round in this cycle of surging and slowing. So we used satellite imagery to take a look at the glaciers and the landscapes, so we knew what to expect and what we expect to see when we got there, and to make sure that we visited lots of different sites representative of the different glacier types on Svalbard. So on the left here, we can also take a look at the satellite images and how they changed over time to give us an idea of how the glaciers behave. So we can see this glacier called Penkbreen is one of those surging glaciers. So its flow speeds up and slows down in a cycle. And when we flick through these images, we can see that in 2011, Penkbreen was quite far up the valley. Its margins are in the lake here, but by 2016 we can see that the margin has advanced into those lakes, and even more so by 2020. So that glacier is now really far down the valley and has advanced during that surge cycle. Now these images on the right of that panel show how that surge has potentially affected the landscape and the geomorphology. So we can see in 2013 Penkbreen is terminating in that large lake. By 2015, it's starting to flow and break apart into the lake, releasing chunks of ice. And when we arrived in 2022, we can see lots of sediment in that lake is being pushed around, creating these mounds of mud, which have been pushed and squeezed into the cracks in the ice as it's advanced over those lake sediments, creating these sharp crested areas of sediment in the landscape. So using these satellite images and previous researchers' work, we were able to identify some key glaciers to visit, which cover cold-based, warm-based, and surging glaciers, to see how their geomorphology and overall land systems differ. Once we have a plan of where to visit, a key consideration in working in such remote environments is thinking about wildlife safety and planning. So as well as hosting a lot of glaciers, Svalbard is also home to around 3,000 polar bears. So it's actually the law that if you're travelling outside of the main town of Longyearbyen in Svalbard, you have to have a rifle for bear safety reasons. So for our project, we needed to make sure we had rifle trained members of the team and that everyone was aware of the risks and safe practices. Working on a boat in this case meant that we didn't have to worry too much about camping safety, but being out close to the ice during the day for field work meant that we always had to be vigilant and aware of those wildlife risks. And that's the case with any wildlife that you might see, as well as having a general respect for the environment that you're working in when working in the Arctic. So a key part of a successful field trip is making sure that everyone is fully trained up and aware of those safety protocols before you head out into the field. Now the next step in the preparing for the field season is probably the most stressful part, which is the packing and logistics. So we need to make sure that we have all of our science equipment. So in this case, we need GPS, sampling bags and rock hammers and uncrewed aerial vehicles. And on larger campaigns with lots of different people working on different projects, this can sometimes mean working through warehouses full of kit for a few days and packing up and logging that equipment before deployment. Working in the Arctic also requires preparing for the cold but not wanting to overheat. So enough room in your luggage for lots and lots of light layers so you can fine tune your temperature on any given day is really important. One minute it can be horizontal snow and rain, and then the next absolute blaring sunshine. So preparing for all weathers is really important. And once all of this is done, we have some of those sites to visit. We've done some wildlife and general expedition safety training. We've packed up our science and personal gear. It's time to finally get out on fieldwork. So we had about 2 weeks on board this ship, the Ula Rinman, and we travelled between different glaciers, visiting a new glacier every day. So after a couple of years of lockdown, I was very happy to finally be back getting stuck in the mud. So every day had some structure to it. So we took notes of the landforms we were seeing using GPS coordinates and sketching and mapping. And then we were flying drones to get aerial views of the landscape and look at how all of these landforms interact with each other. And we took lots and lots of georeferenced photographs, which means that the photographs have GPS coordinates attached to them. So when we upload them to some mapping software, we can see exactly where they were taken and then identify the landforms that we were seeing in the field. We also performed analysis of the sediments. So we collected sediments from the landform features that we were interested in, and they were to be taken back to the lab to be analysed for particle size analysis. And we also took measurements of some of the larger rocks there as well. So we looked at their shape and size in geology, and that would tell us a little bit about the transport processes that they had undergone before and during their formation. So this is what a typical day would look like. The first step was to look at the landforms in the landscape. So here we have a selection of photographs from Buchanan Bream, which is one of those surging glaciers that cycles between fast and slow flow. And we were able to find a load of different subglacial landforms and other indicators of warm-based glacial conditions. Visiting these sites in person helps to give us a real idea of the scale of these landforms as well. So this allows us to get into the detailed analysis of the rocks and the sediments, which we can't get from just looking at aerial and satellite imagery. So here on the left, we have some flutes that are emerging out of the subglacial zone. So we took some sediment samples to check the particle size, and we also did some rock size and shape analysis too to give us an idea of the transport processes. At Buchanan Bream, we also found one of the largest landforms that we mapped across the whole season, and this is an esker, so in the photographs in the right, and this is the outline here in pink, and this is what it looks like above using a drone. And these eskers form where glacier meltwater is able to flush sediment into a tunnel or cavity beneath the ice. So for them to form, we need lots and lots of water and sediment available to create this scale of subglacial landform. So there's a lot of erosion and deposition going on underneath this glacier. To support some of our analysis, we also did some UAV surveys as well. So we had to wait for really good weather. We can't have too much wind, too much rain. And that allowed us to get some more detailed information about the landscape like we have in this picture here. So again, this is from Buchanan Bream, and it's looking out towards the neighbouring glaciers Polar Bream and Scoil Bream. We can see that big esker again in the bottom right, but we can also see lots of outwash and squeeze sediments around here, which are key for identifying a surging glacier. We also launched those UAV surveys to undergo a transect to create digital elevation models. So we take overlapping photographs with the drone from different perspectives, and then in software we're able to stitch those photographs together to build a 3D structure of the landscape. We then use that to help us identify more landforms that we might not have been able to visit directly during the field season, but we can also see some of those smaller landforms that aren't so clear on the satellite imagery. To fully understand the geomorphology of the glacier sites and how their landforms are created, we also collected sediments and rocks to support our analysis. So the sediments that we bring back to the university then undergo particle size analysis, whereas the rocks we collect and describe in the field. So we're looking at the geology, and that tells us whether the rock has been transported locally or from a very long distance away. We can then look at the size, so is it large? Has it required a lot of energy to be moved around? And then what kind of shape is it? If it's quite rounded, it means that it's undergone a lot of smoothing and potential water erosion. Whereas if it's more sharp and angular, it's potentially travelled not very far distances and it's not undergone a lot of those smoothing and erosional processes. And this all aids our interpretation of the processes that have formed the landscape to link back to a wider land system. So after 2 weeks of collecting data and in-field mapping, it was time to head home and begin the hard work of data processing, satellite imagery mapping and laboratory work. The first step was to transpose all of the landform data using GPS coordinates, those UAV photographs and georeference photographs to trace over the key features in the landscape. So in orange on the pictures on the left, we used primary satellite data to map the tops of moraines, which mark the previous extent of the glacier down the valley. In the top right here, we mapped meltwater channels, which indicate the glacier is warm-based and able to produce meltwater that feeds out into the landscape. And we were also able to map patterns of sediment deposits as well. So these deposits on the bottom right in purple are from Pink Breen, one of those surging glaciers. And that shows recent pushed and squeezed sediment landforms with isolated lakes between them, and they formed due to the recent advance of that glacier down the valley. The next step was to analyse the collected sediments. So first we have to remove any residual organic compounds from that sediment, and we do that with a weak acid, and that dissolves any plant material or other organic material that would affect the weight and therefore the reliability of our results. We then dry the sediments out and disaggregate them. So we remove any clumps, but very gently so that we don't crush the sediment particles and affect their particle size. And then those dried sediments are sieved by hand using a column of sieves here. So each compartment has a different aperture size. So the different size grains are kept at each level until we're left with the finest clays and silts at the bottom. The sediment in each compartment is weighed so we can see how much is kept at each size. And then the very fine silt and clays is measured with more specialist equipment. So we use a machine called a masticizer that uses laser beams to measure the amount of light scattered by those particles. And then the different sizes create a different level of scattering. So that can then tell us about what particle sizes are in our sample. Then when we combine that all together, we can start to identify the landforms and the geomorphology of individual glaciers. So here we have an example of some squeezed sediment landforms from Buchanan Breen, one of those surging glaciers. And the shape of this landform, so the very sharp crest at the top here, its height being about 1.5 meters tall, and then the pattern of the sediment size and class shape tell us that this is a crevasse squeeze ridge landform. So crevasse squeeze ridges form mainly in surging glaciers where any fine size soft sediment that's saturated, so there's lots of meltwater at the bed, is squeezed into cracks in the ice that have formed due to the fast flow. So they typically have quite fine sediments in them because they're squeezed into these very small cracks in the ice. So this first bar chart here shows a lot of fine to medium sized material. So in this graph, the higher the number, the finer the particle size. And then in the second chart, this says that the rocks that we measured are an SA or SR shape, which means they're either subangular or subrounded. So they still have some of these sharper edges because they've not been transported very far from the bed. Now we have an idea of some of the landforms and how they were created, we can start to make those geomorphological maps with our data sets. So I personally use ArcGIS for my mapping, and that has a number of tools that also help me to analyse some of those features that I've mapped, like the size of certain landforms, and then overlay all of the data that we've collected to start to get a really holistic analysis of those landscapes. So here is an example of how we can measure a landform using that mapping software. So we've got the landform of interest. In this case, we are going to look at that really large esker that we found at Buchanan Breen, which we are able to quickly identify with the satellite imagery just because of how big it is. And we can do a number of analysis on this. So here we're measuring its size, and we can see it's about 3,000 meters or 2 miles long, so it's pretty big. And we can use that tool with a number of other different landforms in the landscape as well. But we can also view our UAV dataset from that survey that we did. And this lets us look at some of these smaller landforms in a bit more detail. So again, we can zoom in to get some really nice information of these smaller landforms, and we can use that measure tool to measure their size and compare that to that large esker from Buchanan Brain. So you can see in terms of their length, they are coming out at tens of meters, so much smaller than that esker. And then if we turn off that layer, we can see that by measuring this kind of detail is only possible with those UAV surveys because the satellite imagery just isn't good enough. So this is ideal for looking at those smaller landforms like the crevasse squeeze ridges that we looked at and individual boulders as well. So we can see some real improvements in the amount of detailed mapping that we can do when we incorporate UAV data sets into our analysis. So after we've used the sedimentology and aerial and satellite data to identify and trace all of the landforms that we see in the glacier landscape, we get some final products that look something like this. So these are two examples of geomorphological maps of different glacier types from Svalbard. And what we've done here is we've just coloured in each part of the landscape based on what landforms that we found there. And we can see that the geomorphology in these two sites is very different. So on the left is one of those surging glaciers, so this is Penk Brain, and there's a lot going on, so there's lots of subglacial deposits like outwash and ridges at the very far valley margin, so towards the fjord, as well as those squeeze sediment deposits close to the ice margin. And this all indicates contemporary, present-day, warm-based, fast-flow conditions. So there's lots of meltwater readily available in this glacier for erosion and deposition. Now looking completely different on the right, we have Ferdinand Brain, where here the main landforms are moraines, and these mark the past extent of the glacier. So this tells us that it used to fill out this whole valley here and was previously able to erode and transport sediments at the margins. Now, however, this landscape is full of bedrock and very thin deposits, which we call sediment drapes. But the most important thing that this map shows us is that the ice, the main glacier ice, is chunky and fragmented. So this glacier is receding and it's disconnected and wasting away. So there's not enough ice to continue flowing for much longer in this glacier. And there's definitely not enough ice to create enough pressure for the bottom of the ice to start to melt. So it's completely frozen to its bed, and that's why there's not a lot of subglacial landforms in this geomorphological map. And closer to where the ice margin is, there's very little geomorphology for us to map as well. So once we've got those geomorphological maps, the final piece of the puzzle was to take all of the glaciers that we looked at here to create a diagnostic land system of the different types of glaciers that are found in Svalbard. So these land systems cover all of the key features and landforms that we see at the groups of the different glacier types. So in this case, warm-based and cold-based glaciers. And we can use these land systems to diagnose the glacier style at other sites as well, based on what some of the key landforms we see in their forefields too. So this gives us the broad information about what the different glaciers on Svalbard produce in their landscape under those different flow conditions. So here on the left we have lots of subglacial landforms in a warm-based glacier land system. So lots of those flutes and eskers and outwash plains as well, which all indicate that there's a lot of meltwater present. So those glaciers are able to melt the water at their base and then create erosional and depositional landforms in the landscape. Whereas in the cold-based glaciers, like Ferdinand Brain on the right, we have a lot of bedrock outcrops and fragments of glacier ice. So these glaciers are actively receding and starting to disintegrate. So the landscape's dominated typically by moraines from when it was more active, and then thin till cover and deposits. And these land systems can help us to understand how the glaciers will continue to change under a warming climate as they link their geomorphology to their formation processes and the wider climate system. So for example, as glaciers melt and recede, are we more likely to see these thin, fragmented cold-based glaciers in the future? So we're more likely to see glaciers that look a lot more like Ferdinand Brain. But also, how will glaciers' current dynamics affect how it responds to climate change? Do those cycles of fast and slow flow and surging glaciers also impact on how vulnerable it might be to climate change? And the first step to start answering these bigger questions is by doing some mapping projects like this, where we can start to stitch together some of those glacial landforms and their formation processes to look a bit deeper into their glacier dynamics. So this is a really critical step in understanding the current glacial landscape and providing context to wider work. So in the case of this Svalbard project, while we were out there, we were also looking at the microbial communities and the geochemistry beneath these glaciers as well. So this mapping work provided some really nice context to some of the results we saw in that side of the project as well. But these land systems and geomorphological maps can also provide some valuable insights into the future of glaciers and their landscapes just on their own as well. So I hope I've been able to give you some insight into what a mapping project looks like in terms of glacial geomorphology and land systems, and how mapping is actually just the first step in allowing us to answer some big important questions about how glaciers respond to climate change.
Hi, Becky. Thank you so much for sharing your work with us on glacier geomorphologic mapping. Lindsay and I are so excited to talk more with you today about your work. And just a reminder for the audience, if you are tuning in live during the premiere, Becky is available to answer the questions in the chat, so feel free to interact with her there. So Becky, we'd love to hear more about your schooling. Are there any courses you took that prepared you for the work that you're doing today? Are there any courses that influence your studies more than others that have led you to where you are now?
Yeah, so it's kind of by chance that I ended up going to a local university, and they have a real focus on polar science in general. So it's very research focused learning. So we kind of build off of everyone else's expertise. So it's kind of a natural progression to go down that polar science route. And then we also had quite a strong GIS remote sensing program as well. So I did all of the GIS courses because I was just obsessed. I really liked the mapping and the problem solving with maps. It was really great. So I've kind of tried to incorporate that throughout that whole degree and then carried on through my work as well.
Great. So what about in terms of the equipment that you use in the lab? Like you showed is it called a master sizer machine? Yeah.
Yeah.
So like, did you have a lot of experience with that in schooling, or do you get a lot of on-the-job training for those?
So we do quite a bit of laboratory training as part of the course. There was quite a bit of geology, sedimentology components to some of the undergraduate courses there. So I had a little bit of experience, but usually we do a lot of on-the-job training as well. So if there was a particular aim that I wanted outside of the mapping part of the project, then my process is usually to go read some papers, see what other people have done, if their aims are very similar to mine. And then I'd take that to an academic in the department that I know might have worked on something similar before, or to our laboratory technicians, which are great. They seem to know everything, and they normally train us up on the more specific techniques like the master sizer when we need them.
So it just makes me think that if you're doing research on these techniques, do you have connections with other universities maybe that you work closely with or could reach out to easily to get more information?
Yeah, so we tend to work a lot with our collaborators universities as well. So I have a collaborator at Newcastle as part of this project. So being able to go and use their facilities if we don't have some of the very specific equipment that we need to sort of fulfill the project, it's quite easy to go and work somewhere else as well. And it's that kind of collaboration that I think is really important in the sciences in general.
Yeah, the collaboration aspect to get ideas for projects and to make those connections at different conferences. I'm sure you have lots of experience how you're able to network with different professionals. And so I wonder, for all of our younger early career professionals and students, what are some of the tips you have for those sorts of collaborations and connections that you could make?
Yeah, so I think for me especially, I've been in the same institution my whole career. So being able to get external collaborators is really important. Especially in academia, there's kind of, at least historically, been a lot of push to work at different universities in different parts of the world to meet new people and get new ideas. But I think you can really do that by going to conferences, speaking to people that say you introduce yourself because you've read their paper that you find really interesting, and build conversations that way. generally at conferences, there's tons of coffee breaks. So trying to grab someone at a coffee break is always a really good idea. But building those collaborations is actually super important, especially in academia, because then you work together and you write grants together, get funding, and then build on your own projects.
That's awesome. Thank you for that. Now, kind of diving more into the actual presentation, you discuss a lot of differences between the cold-based and warm-based glaciers and the landforms and features they both create. Are there specific locations where you are more likely to find a cold-based versus a warm-based glacier? And if so, what environmental conditions are most influential in determining the type that forms?
Yeah, so cold-based and warm-based as a term refers to the glacier thermal regime. So that's the temperature that you get at the bed of the glacier. And a lot of these glaciers can actually be a mix of both, and they're often referred to as polythermal. So a lot of the Svalbard glaciers actually fall in this polythermal category. And that means there's either spatial or temporal differences in that basal thermal regime. And that's kind of a function of the ice temperature, which is affected by the surrounding air temperature, and as well as the ground. So if you think of places like Iceland, there's a lot of geothermal heat there, which kind of drives those ground temperatures up a little bit. And as well as the air and ice temperature, you've also got pressure from how thick that ice is as well. So if you've got really thick ice, it's quite heavy, it can start to generate heat at the bed as well. So in terms of warm-based glaciers, you're more likely to get them in places like the Alps because of those slightly warmer air temperatures. And we're more likely to see these cold-based glaciers where those air temperatures are more consistently low, or where the ice actually might be thinner. So some of the work that we've done in Svalbard, we can actually see that the glaciers are melting and thinning because of climate change. And some of the glaciers that we investigated as part of this project had melted to such a point that they were so thin, they're starting to exhibit these more cold-based states rather than their more general, like historic polythermal states. So really, it's a bit of a balance between sort of pressure and air temperature. And even in the same region, you can get a cold-based glacier next to a warm-based glacier in Svalbard. It's a complication beyond my knowledge, that's for sure.
All right, Becky, you kind of mentioned this or alluded to it, but Arctic Svalbard is especially sensitive to climate change. And can you elaborate a little bit more as to why this is?
Yeah, so Svalbard is located in the high Arctic. So very broadly, the high Arctic has quite extremely low winter temperatures that kind of persist for much of the year. But Svalbard is also impacted by the North Atlantic warming current, which is kind of a warm-based current that flows north, past the UK, past Scandinavia, and then around Svalbard. And that kind of brings more of a maritime climate to Svalbard. So it's kind of enhancing some of that Arctic amplification that we see with climate change. It's buffering some of those typically like very cold temperatures that we normally see in the high Arctic and driving a lot more of these anomalous warm temperatures, especially in their wintertime.
So I imagine those changes are then causing changes within the glaciers themselves. And so during your presentation, when you showed the animation of the NASA Earth Observatory and how glaciers change over time, I was wondering if you could kind of walk us through that, talk about how the animations are made, and then point out some specific features that you could study using these images.
Yeah, so NASA has quite a lot of these really cool animations of the cryosphere. They use a lot of Landsat satellite imagery. So I think this particular image is Landsat 5 and Landsat 7 satellite images. And these kind of animations can help us see how a glacier flows, so we can see how it sort of interacts with the landscape, and how it changes. But here we can especially see the formation of these glacier moraines, which kind of mark the maximum extent of a glacier. So we can see that as the glacier moves forwards, these moraines are forming at the margin as these kind of brown ridges as that glacier flows and pushes some of that sediment up into these almost like hill shapes. And then remote sensing specialists can use all of these data sets and the time series that they were taken on to determine things like ice velocity as well as some of the behavior changes that we see as well.
Great, thank you. And talk a little bit more about your experience there. You talked about that your expedition to Svalbard took about 2 weeks. So how much wiggle room is there in the length of that expedition? Like how much planning does there have to do? Like how like down to the minute are you with that work?
So it kind of depends. In this case, our flights were booked well in advance. So kind of the full length of time that we have there isn't necessarily flexible, but we can kind of change our plans as we go. So we typically try and allow for, because we were ship-based, so we were going to be on board for 10 days out of the 2 weeks. We had 2 days in Svalbard before we got on the boat and 2 days after. And that kind of allowed for any issues like luggage not arriving on time, or the ship not being able to get us home in time to make our flight. So when we're actually on the ship, it's a lot more flexible. We planned to visit a different glacier every day and then move on to the next location. So we'd spend one day at one particular site and then we'd get on board the boat and the captain would drive us to our next glacier for the next morning. So there was room there to maybe spend 2 days at a site if we found it particularly interesting. Say we wanted to collect some more samples or try and do some more drone imagery because that was very weather based. But for us, one day was pretty much ample for everything that we wanted to do. So the main real critical deadline here was just getting the ship back to Longyearbyen on time because they definitely had more scientists on board straight after we were finished.
So was it a research vessel specifically?
It was a charter vessel, so they have like film companies go on board sometimes to do documentary filmmaking, but they were quite a recent company. I think they've been going for maybe 2 years when we joined, and they're trying to build up their science base. So I see them posting a lot of adverts,
Great,
and
great.
I really want to go back.
Oh, well, I'm sure they would be welcome to have you.
It's
Um,
fantastic.
Yeah, but you also mentioned there's multiple teams on there. So was there any crossover or overlap in the work that was being done among those teams? Like, were you kind of collecting samples together, or is it something that relates to all to glaciers?
Yeah, so we were a team of 5 with 3 different projects and one field guide. So his responsibility was primarily just like, don't let us get eaten by polar bears. That was his one job. Um, so because Svalbard is quite risky in terms of polar bears, it was a no-go in terms of splitting up. So we did everything together. Um, so the mapping project was very glacier based, obviously. So we do a mapping as we walk down the forefield towards the glacier. The microbiology project, there was one that was sediment based that I led, and that was collecting sediments at the glacier margin. And then another one was the air, the microbes in the air around the glacier. So again, we were all kind of going towards the same goal. And it meant that when we were walking to site, we could do some mapping. And then when the microbiological data collection was going on, the mapping team could start flying the drone and getting some nice drone images rather than standing around in the cold waiting for us.
I love the fear of, I mean, obviously it's a real threat. They're real polar bears. So I'm glad that you got a field guide with you to take care of everyone. But I can imagine all the loved ones at home it's being like, oh, great. Take a boat, go and do some research with the polar bears. It's
Yeah.
awesome.
Having a
Um,
boat is great though because you get to get straight back on board. There's no tent, no cabin.
yeah.
Those bears are not getting on that boat.
Yeah, that's definitely true. Definitely true.
Mm.
So speaking of drones, and you last mentioned that the mapping team was kind of in charge of that. Is everyone trained on the drones? So if there is an instance where the weather cleared up and someone was busy, another person could pick it up, or is there a specific person that was kind of in charge of the drone work in the expedition?
Yeah, when we went out, there was one person that was kind of the drone expert, and it was her drone that her personal drone that she brought out with us. She did train pretty much everyone that was interested. She trained us up so that we all got a chance to fly a transect and use our own data sets, which was really nice. So I'm not like super 100% confident on drone operation, but I have managed to take some of the things that she taught me on this expedition to my current project in Greenland and do a little bit of drone imagery there as well, which is super nice. Keeps the knowledge fresh as well.
That's great. Um, And speaking more about training, not just with a drone, but you talked a little bit at the beginning about your ArcGIS training. But are you uploading your data to ArcGIS? Does it become available for others? And like how much training did you have in order to be able to, do all the processes on ArcGIS?
Yeah, so in terms of the training, the undergraduate degree I did was pretty comprehensive, and it was a really great start in getting to know the language of the program. So even though I wasn't trained specifically on geomorphological mapping, I'm able now to sort of read a paper on it and then know what that language is and know how to search for the information to learn how to do it. And to be honest, things like YouTube for tutorials, especially with any kind of software, is an absolute savior. And I really believe like if you want to learn something, you can, if you put your mind to it, you can learn it when it comes to software and these kinds of skills. In terms of data uploading, I the sort of coloured shape files that I made of all the different landforms, they aren't uploaded to ArcGIS, but they are available online on a data repository. So anyone with either ArcGIS or any other GIS software, they can download those shape files and upload it to their own program. And they can make their own interpretations and edit it as they see fit.
In terms of all the different colors and different maps that you've created that highlight all these features, when you were taking those measurements, could you show us where some of those samples and measurements were taken, or where some of the key features that you captured are to help make those images and maps?
Yeah, so we did a lot of the mapping, the final mapping after the fieldwork, and we used a lot of the satellite imagery as kind of a base. And then all of the photographs that we took were geo-referenced, so we could upload them to GIS and then see where they were taken to see what some of those like big features are, like that giant esker that we mapped. That was a really easy one to find even on the satellite image because it's absolutely huge. I've seen nothing like it. Um, but things like the small crevasse squeeze ridges, that was really important to see in the field and get GPS coordinates of so that we could map them more accurately on the software because you can't see them on satellite images, they're far too small. So things like crevasse squeeze ridges and some of the smaller moraines or ice core features, you need to really see them on the ground, get the GPS coordinates of them, and then start to upload them to the map and colouring in some of that base map imagery.
So after mapping a glacier, is there a plan to monitor it or revisit it to see how it continues to change?
So that's not in our plans at the moment, unfortunately, although I'd love to go back, especially on the boat. But the great thing about the increased availability of some of these sort of satellite data sets is that we can start to monitor those changes remotely as well. So now we've got some glaciers of interest, especially those ones that I mentioned before, the ones that are going from those polythermal conditions to more cold-based conditions. They're ones that I really want to try and keep track of and sort of see what they're up to. So with these satellite images, we can trace the outline of the glacier, especially the glacier front, and then see if it starts moving back over time. And we can map the retreat and any new landforms that might be coming out of those glaciers as well. But that's not to detract from how important it is to go and see some of these things in the field as well, because ground truthing is a very important part of the mapping process.
I know, and we've done fieldwork in the past with the ground truth, and everyone's like, "Oh, you have technology nowadays. Do we need to actually have boots on the ground?" And it's so important to reiterate how important it is to validate these results and really get on the ground to see the changes. So I'm glad that you emphasized that as well.
Yeah, you can't see the things in 3D like you can in
Mm-hmm.
person. Some things are super small and things change, like meltwater channels, especially, they'll redirect, go wherever they want to go. And if that satellite imagery is not up to date, then you're not getting a true representation of the landscape, I think. Yeah.
Great. And then speaking of, obviously you mentioned wanting to get back on a boat. It was an enjoyable experience for yourself, but what other maybe most interesting or surprising features or data did you measure or did you experience while on a trip like this?
So I think the whole trip was, for me, it was my first ever bit of polar field work. So the whole thing was brand new and just eye-opening. The most memorable part was flying into Svalbard and seeing my first glacier, even if it was from the plane. That was super exciting. Once we were in the field, I think that giant esker was crazy. I loved it. I feel very attached to this esker. And then in terms of some of the sort of more surprising features was definitely these very small crevasse squeeze ridges because we weren't able to see them before we went out there, and being able to see like fields of them. There was hundreds of them all in these little like contained locations of just little muddy mounds. It was really interesting. I love that.
So, were you the first team to map this particular glacier?
We are the first for I think a few of them because
Okay.
we mapped 10. So some of them will be the first time they've ever been mapped. Some of them are, I can't remember off the top of my head which ones are an update. I think they were last mapped maybe in the 90s or early noughties. So yeah, we've got a nice paper out of all of the colourful maps. Um, but yeah, some of them I don't think people have ever been to them before. So it was really cool.
Yeah, and you touched on this already, but you looked at the geomorphology of the area, but also worked with a team who was focusing on geochemistry and microbiology around the glacier. Um, so are you all strictly in your own fields, or do you consider it more like interdisciplinary, where you're each kind of like touching on each other's work, and maybe calling in other specialists as needed?
Yeah, so my specialty is pretty interdisciplinary in itself. So my sort of role on this trip was the microbiology and the geochemistry, and then I dipped in a little bit in the mapping because I'd had that prior training. So although we had a mapping specialist with us when we got back, a lot of that mapping and the GIS stuff I was quite comfortable to sort of take on. We also had a more experienced microbiologist with us as well, which was really helpful, because that stuff can get super complicated super fast. So having someone with you that knows the ground, like knows that field work, to ask important questions on the ball was super helpful. Um, but when we're in the field, it's so remote, we don't have communication outside. So if you don't have that expertise with you, then you're just gonna have to try your best.
Yeah. But then also, were you able to do any analysis kind of like in the moment and maybe make some last minute decisions about where you would take some data? Or what did that all really wait till you got back to the lab?
So we did a lot of the sediment analysis in the field in terms of sort of the rock morphology, the class shapes or the roundness and the angularity of some of the rocks that we saw in like particular landforms. So we were able to do that in the field, and then the rest, everything just kind of got bagged up and taken back to the lab. In terms of prep, because we were picking glaciers as we kind of went around the fjords to see what was accessible. So we didn't really know for sure what glaciers we'd be visiting every day either. It was kind of a very much you got to see whether the moraines are even small enough to get over and to get into the full field. So a lot of that analysis was done kind of, ad hoc.
And Becky, it's clear that you enjoy this work. You're obviously enthusiastic about the work that you're talking about. And I wonder, are you doing similar work now, or is there a new project that's exciting you that you're off doing instead of this glacier morphology work?
So I'm doing a little bit of work in Greenland at the minute. So I'm doing a bit more of the geochemistry rather than the mapping. And we're looking at chemical weathering signatures coming out of the Greenland ice sheet, which is really cool. So we got to do a lot of field work over the summer and the spring. Don't recommend it in the spring, it's very cold. Summertime, much nicer. But yeah, so that is my sort of current position. That ends in July. So after that, I'm looking for my next postdoc position and applying for some of my own funding as well to try and establish my own sort of permanent position somewhere so that I can keep doing research and a little bit of teaching's nice.
But it sounds like you're sticking in the polar regions for the work that you're hoping to do in the future.
I hope so. I do complain about the cold, but I don't mean it really.
You've
I
got to
love it.
complain about something, right? And that's just inherent in a polar expedition.
Yeah, I'd honestly, much rather be in the poles than somewhere hot. I can't deal with the heat. You can always wear more layers.
True. All right, and Becky, and as we're wrapping up for today, I wonder if you could talk about some of your professional goals that you have for the future and maybe what's next for you beyond the next 6 months in Greenland.
So I really want to stay in academia. So doing polar research is generally my big goal. I'm trying to apply for my own funding to try and establish some of my own projects again through some of those like collaborations that we build at conferences and building on some of the ideas that I've managed to collect through my postdocs and through my collaborators, try and build on a bigger project that I could potentially lead. Um, but with the contract ending quite soon, I'm in the market for another postdoc, polar based, glaciology based, geomicrobiology is always a good shout. But continuing on some of the mapping work is, I think, a really important part of this part of the polar research because it provides some of that really important context to some of the other things that we're studying. So this microbiology work that we did in Svalbard, we're able to provide context of what that glacial system looks like and how it might influence the microbiology because of what we see in the maps and what we see in the landforms. So I want to continue to take my GIS skills around the poles and map everything.
And because you'd like to stay in academia, do you have teaching experience? Would you like to have teaching experience as well?
Yes, I've got quite a bit of GIS teaching experience, and I'll continue that while I'm still at the university that I'm at the minute. But again, I'm happy to kind of expand out some of those teaching skills into some more lab-based projects and things like that as well.
Awesome. Well, thank you so much, Becky, for talking with Lindsay and I today. We really appreciate you taking the time to present and share your work with us. And for all of you that interact with Becky in the chat, thank you. And if you have any questions for Becky beyond what she was able to answer today, or that maybe come up after the live premiere, feel free to email us and we will get the questions to Becky. Great. Thanks so
Thanks
much,
for having
Becky.
me.
Thank you. Thank you to everyone who attended the live viewing of today's webinar. The recording and chat will be available on AGI's YouTube channel immediately following this event. For information on additional webinars from all of AGI's webinar series, please visit our website at americangeosciences.org/webinars. Applications are now open for early career professionals interested in presenting in an upcoming webinar. If your work involves the creation, analysis, or application of maps, showcase your skills and connect with a broader audience by becoming a webinar speaker. To access the application, scan the QR code or click on the link in the chat.